My name is Ana Paula Piedade. I'm from the University of Coimbra in Portugal, and I want to talk you or show you a little bit what we have done when we consider the defects on components produced by additive manufacturing. Yeah, in fact, just let me show you where I am. I am here in Europe, okay? I'm Portugal, just the west end of it. And just to show you a little bit, I am in Coimbra, which is part of the central region of Portugal. Here you have Nazaré. Probably you heard the biggest waves in the world for surfing, 100 feet, okay? And my university, which is in Coimbra, between Porto and Lisbon, it's one of the oldest universities. As you can see, it was founded in 1290, okay? And since 10 years, we have been the World Heritage for UNESCO. But nevertheless, although I'm online, I must tell you that I was born in Figueira da Foz, which is a town over here, a beach town, okay? And if you go straight from Figueira, always ahead through the Atlantic Ocean, you'll go straight to New York. So from those of us that are in Europe, I'm the closest one to the United States. Okay, nevertheless, let me go through what brought us here. So in order, because this work was like a challenge, because all my colleagues are always telling me, yeah, additive manufacturing, but yeah, but that's a lot of defects. And really, I was a little bit already sick of hearing them. So I tried to take advantage of a problem, which means that I would not face it as a problem. I would take advantage of that problem, let's say. Okay, so I tested different roughness with increased defects, in this case porosity, with two different materials, two different shapes. For what? As you know, and as probably you saw in the map, Portugal is a very small country, but we own, let's say, a lot of water in the Atlantic Ocean. Why? Because we have Açores and Madeira, which are the islands, and Açores is at the middle between Portugal and the United States. So we have a lot of water. And nonetheless, we are experienced all over the world very long periods without water. We in Portugal actually are in a crisis of heat waves, and then we have very few water. And on other parts, you know that it's raining catastrophically in our Spain, which is near here, Portugal. So we need to find a way to to take the water and to reuse it in very sustainable ways, just not sustainable for materials, but sustainable for our main, things for living, just like water. So why we did this study? In the first case for water oil separation without any chemicals, just a physical separation. And then because of the results of first case, we had some ideas and went for a second study. Also, we have the motivation because my university is the first more sustainable Portuguese university, and it's the 22nd, in the world. So also having some sustainable approach to our resources, such as water, can contribute to maintain or to even increase the sustainability of the university around the world. So, because this was not supposed to be like this. Sorry, I'm sorry. It was really, the animations just didn't work. Okay. Well, how did we did the different surface roughness? Because it just hit me one slide. We had high quality and low quality printing. So we had 300 microns of layer high, and we had 100 microns of layer high. Just by doing that, of course, you are increasing the roughness of the surface, and also you are increasing the defects. Also, we are choosing two materials, and the materials that we are choosing are EPS, high-impact polystyrene, which is a known, very well-known copolymer, and we were also making the same printing with a commercial foam filament. Okay, so as those that are registered marks, most of the times the manufacturers do not say what it's in the polymer. Okay, but we had master students that went through this polymer, and we kind of sort out that it was made from PVA. That was announced, and the other part was TPU, so polyurethane. Okay, so what we do with this foam material, because it has PVA, we all know that PVA is soluble in water. Okay, so this is the micrographs of the foam filament before and after being washed in water. So as you can see, we are already increased the defects, in this case the porosity, of the filament itself, which means that once you have the components 3D printing with this material, you will end up with a hierarchical porosity. So you have the macro porosity, which is given to you by when you choose the layer height, and you have a micro porosity, which will be enhanced by the removal of the PVA. Okay, so what in case one did we want to do? We wanted the objective to make like mechanical separation of a mixture of oil and water. Okay, in principle, if you have a super oleophobic mesh, that super oleophobic mesh will retain the oil and let the water flow. Of course, on the other hand, if you have a super hydrophobic mesh, it will retain the water and will let the oil pass. And this will be made without any chemicals added, so in a very sustainable way. And of course, if you have something, a material that is amphiphilic, you will have like a mixture of both behaviors. Okay, so what did we do? We had the hips, and we tried two shapes with the same area that was exposed to the water after. Okay, and these shapes was supposed to go in a column, and that column will be separated in stages by also 3D printing hips or foam meshes, okay, with different infill, different geometry, just to see which one was more appropriated to enhance the mesh behavior and separation from the materials. Okay, so of course, because foam has PVA, which is soluble in water, what we did first was to remove the water from the foam. Nevertheless, you need to characterize everything that you buy. Why? Because you really don't know if they are selling to you what you're really buying. So IPS, we made a characterization by FTIR, and we saw that it was corresponding to a high impact polystyrene filament, and then we made it with foam in red and wet foam, so after PVA removal. In fact, you see, and it's not just because all the peaks are with less intensity. In fact, you have a decrease on the OH peak and on CH peak, which are corresponding to the PVA. Okay, then we went to water sorption. And of course, you have here on black IPS, and you have foam in white and washed foam in blue. We must consider this with some careful. Why? Because when you have foam, not washed foam, what it happens is that they are taking water, but at the same time, then they are losing the PVA. Okay, so you have a balance between these, and if you do this in a non-continuous flow of water, always in the same volume of water, at one time, you do not have PVA being leached out because it reaches an equilibrium with the PVA inside, okay? But what you can see here is that after being washed okay, wash it, sorry, you really have a very high percentage of water absorption. That's good because if you want some interaction with water, it was needed. Okay, also we made, in order to choose our temperatures for printing, we made also TGA and DSC studies of the filament, and you have here HIPS, and you have the derivative of the TGA, and you have for non-washed foam. As you can see, what you have, it's here the physical bond water, and you have PVA, and then you have TPU as expected, okay? For the DSC, what show you is that, as expected, IPS is amorphous, and the wetted foam is semi-crystalline because you have, well, a little bit complex temperature of melting for the washed foam. Nevertheless, you are going to print the non-washed foam because you need some hardness of the filament to be printed, okay? And of course, then you need to characterize it. As you see here, you have IPS and foam. You see really the roughness of the surface due to the low quality, okay, printing. And you have the contact angle with water and with oil of IPS, both geometries. So you have pyramidal in gray and semi-spherical in black. And you have IPS, water, oil, and foam. So IPS is oleophilic, hydrophobic, while looking at the contact angles of foam, mainly in the pyramidal shape, you can say that it has an amphiphilic structure, okay? Because the contact angle in water and in oil, it's almost the same, okay? Once again, because contact angles are very dependent on the roughness of the surface, and they are very altered, our equipment that measures contact angles, it also determines the surface roughness exactly in the same point where it's going to measure the contact angle. So you are able to measure the roughness factor, you are able to take the surface roughness parameters, such as in this case, the average surface roughness with 27, as you can see, very high, 27 and 31 micrometers, and you have a correct contact angle regarding the surface. And it is here demonstrated for HIPS, both geometries, and as you can see, it's almost the same value. The geometry does not have influence, it's the chemistry that has. We made the same thing for water and oil, for IPS, for both shapes, and the contact angles after correction with the roughness, sorry, okay? And then we have also the values of the surface roughness, just to confirm that, of course, we had a very high value of surface roughness. In order to characterize, we first made a preliminary studies where we, through those meshes that we have, those membranes that we have to put on the column, we saw what was the best one in order to let the liquid flow. And after having these preliminary tests, what we did was to make two schematic columns for making the test. So the first one, you have a column where you have the membranes and you have alternated spherical and pyramidal geometries, okay? And you have a peristaltic pump that is continuously making the water-oil suspension pass through the column. On another system, we had only the pyramidal samples on the column with some space for the liquid to pass besides the geometric shape, and we made another one with a spherical sample, okay? So the results, what they show us, that the separation efficiency, considering the surface area of each one of them, was very, very similar, IPS for both geometrical, but very dissimilar for both geometrical shapes in foam. And you have a much higher separation efficiency for pyramidal shape than for semi-spherical shape. Moreover, depending on the shapes that you have first the separation of oil and then it begins to have water, or you have first water and then you have the separation of the oil. So first water and then oil. Okay, so depending on the material and also depending on the geometry, you will have a separation, okay? But the sequence of liquids will be different. So at a first glance, it seems that yes, we had some good results. But we want not to make this once, okay? We wanted to wash the samples and redone and reuse it, okay? And yes, we did it by reusing and cleaning those printed samples in distilled water in ultrasounds. However, one day, the students did not have distilled water and they used tap water. And I'm afraid to say that some time ago on a Monday morning, this is what the water was coming out of the taps. And when they use it to clean with this water the components, we saw this. So the pyramids and semi-spheres made of hips were still white. They were clean with no oil, no nothing. But the ones made of foam, they were kind of rose, pink, yellow, something. So this gave us an idea for to study case 2. If I have enough water absorption, may perhaps due to the increase in the defects, which is porosity, may I have metallic ions removal? Well, let's see. First of all, let's quantify if yes or no we have more pores. It's just not to say, oh, we are going to take PVA out of it, then we are going to have microporosity. So first of all, non-drying sample as printing after washing, what you see is an increment of the shapes, of the sizes of the pyramid, because the pyramid was the best one with that pink yellow color. And then when you dry, even the washed one, you see that you do not, well, you have some difference in size, okay? But what you have, it's not very different. Then we took these pyramids, so these are the CT scans, and then we took this pyramid and tried to quantify the increase or whatever, it showed an increase in the porosity. So the total pore area, increased when you remove PVA. You have the medium pore diameter, which also increased when you consider all the pores in volume. When you consider the diameters in area, it also increased. The bulk density decreases, the apparentity density decreases, and of course, the percentage of porosity increase. So here we demonstrate that, in fact, it's just not us saying that we have an increase in defects, in this case, porosity, okay? So we printed the pyramids, we made it like a test column, and we had this beautiful water on a Monday morning, and we started to make our tests. And after some time, what you get is that the pyramids are getting reddish and the water is getting less orange, okay? And as you can see in a qualitative evaluation, this was before the study, and this was the pyramids after the continuous flow study, and this is the collected water, and this was the pyramids after the ultrasound, as I show you, the study, and as you see, the water is like that, okay? But once again, not only a qualitative evaluation, we need some quantitative evaluation. So we made the evaluation by using X-ray fluorescence and atomic absorption. You see that here it's the water before the test, and here it's the water after the test, okay? Nevertheless, you have a removal capacity of the metallic ions in water. The ones that we saw in higher concentration were copper, iron, and zinc. And when you do the quantification by atomic absorption, you see that you have 100% removal capacity in continuous for the copper, almost 100 for the iron and the zinc, always above 80% of removal capacity. When you make the same evaluation by XRF, it's much more simpler, but it's not as sensitive as it is. So you have kind of different approaches, but the zinc, the copper is not detected in XRF, okay? Once again, we also measure by XRF the quantity of the metallic ions that were in the printing samples. And because of some, problems that you have with this technique, even before experiments, you see that you have some of the ions that are detected in the foam, okay? And we think there are contaminants from the support holder of the technique. Anyway, after continuous, you have a lot of iron and zinc on the foam, and after ultrasound, you have an increase in iron, an increase in zinc, but in fact, very small concentrations when compared with the ability of the continuous test. Sorry. So as we have a high percentage of water absorption, and you know that just by